Hello everyone. I'm Sharanya Kumar, and in this video, I'll be presenting my comparative analysis of water purification technologies, specifically comparing reverse osmosis, ultrafiltration, and activated carbon filtration. This project focuses on understanding how different engineering solutions tackle the same real-world problem, providing safe and clean drinking water. Access to clean drinking water is one of the world's biggest challenges. According to the World Health Organization, more than 2 billion people globally still lack access to safe water. The water we use often contains microorganisms, heavy metals, and dissolved salts, which can cause serious health problems. That's where engineering innovations come in, designing efficient water purification systems that remove contaminants and make water safe for daily use. In this presentation, we'll look at 3 key technologies that do this in very different ways. The main objective of this analysis is threefold. To compare 3 important purification methods: reverse osmosis, ultrafiltration, and activated carbon filtration. To understand their working principles, technologies involved, and suitability for different users. And finally, to recommend the most effective or hybrid solution based on sustainability, usability, and feasibility. Let's begin with reverse osmosis, commonly known as RO. This is one of the most advanced and widely used methods for water purification. Purpose: RO systems are designed to remove dissolved salts, heavy metals, and chemical contaminants that most basic filters can't handle. Working principle: in an RO system, water is forced through a semi-permeable membrane under high pressure. The membrane allows only water molecules to pass through while blocking impurities and salts. As a result, you get pure water on one side and concentrated wastewater on the other. Target users: RO systems are ideal for urban households, industries, and areas with high total dissolved solids, or TDS, in the water. From an engineering perspective, RO combines several domains: chemical, mechanical, and environmental engineering. It uses membrane technology, fluid mechanics, and pressure systems. Its biggest strength is high purification efficiency. It removes almost everything harmful. However, it also has limitations. It consumes more electricity, and it wastes a significant amount of water in the process. So while it gives the cleanest water, it's not the most sustainable. Next, let's look at ultrafiltration, or UF. This method focuses more on microbial purification, removing bacteria, viruses, and suspended solids. Purpose: it's designed for water that isn't salty but may have visible or biological impurities. Working principle: water is passed through a hollow fiber membrane with microscopic pores, typically between 0.01 and 0.1 microns. These pores act as a barrier to bacteria and most viruses, while allowing water and minerals to pass through. Target users: UF systems are best suited for rural and semi-urban households, especially where the water has low TDS levels but may not be microbiologically safe. UF is a great example of environmental and materials engineering. It uses polymer membrane design and low-pressure filtration technology. Its strengths are its simplicity and low energy consumption. Many UF systems don't even need electricity. They're also very low maintenance. However, the limitation is that UF cannot remove dissolved salts or heavy metals, which means it's not suitable for highly contaminated water sources. Now, let's move to the third technology: activated carbon filtration. This is one of the oldest and most reliable purification methods. Purpose: activated carbon filters are primarily used to remove chlorine, bad odors, color, and organic compounds from water. Working principle: the filter contains activated carbon granules, which have an enormous surface area. As water passes through, impurities stick to the surface through a process called adsorption. Target users: these filters are common in homes, small-scale water purifiers, and as pre-filtration stages before more advanced systems like RO or UF. From an engineering standpoint, this method uses surface chemistry and adsorption principles, belonging mainly to chemical and environmental engineering. The strengths of activated carbon filters are their low cost, eco-friendliness, and the fact that they improve taste and odor. However, they cannot remove pathogens or dissolved salts, so they're usually used in combination with other systems rather than as a standalone solution. Now that we've seen how each technology works, let's compare them directly. Reverse osmosis removes almost all contaminants, but it requires high energy and wastes water. Ultrafiltration removes bacteria and suspended solids without electricity, but it doesn't handle dissolved salts. Activated carbon improves taste and removes organic chemicals, but not pathogens or metals. In terms of logic, all three rely on filtration, but their mechanisms and pore sizes are different. In terms of usability, UF and carbon filters are simpler to maintain. For sustainability, UF and carbon are better because they don't waste water or require power. And in terms of feasibility, RO is ideal for heavily contaminated areas, while the others are better for moderately impure water. When we look at the broader picture, logic, all three use the principle of filtration but at different scales: molecular for RO, micro for UF, and surface adsorption for carbon. Usability, UF and carbon systems are more user-friendly and suitable for daily use. Sustainability, RO is less sustainable due to energy and water waste, while UF and carbon are eco-friendlier. Feasibility, each system has its niche: RO for industrial and urban use, UF for villages, and carbon filters for pre-purification. Based on the comparison, the best solution isn't just one, it's a hybrid system combining activated carbon, ultrafiltration, and reverse osmosis. Here's why. The carbon filter first removes chlorine and organic compounds. Then, ultrafiltration removes bacteria and suspended solids. Finally, reverse osmosis eliminates dissolved salts and heavy metals. This combination ensures the highest purity, longer membrane life, and better taste, while also balancing cost and sustainability. It's the kind of solution used in most modern multi-stage purifiers today. To sum up, clean water isn't just about removing impurities, it's about choosing the right combination of technologies for your local water conditions. Engineering plays a crucial role here, from designing efficient membranes to optimizing energy use. While RO offers the highest purity, UF and carbon filters make the process more sustainable and affordable. So, the future of water purification lies in hybrid systems that combine the strengths of each approach. Thank you for watching. I hope this helped you understand how different engineering solutions tackle the same essential challenge: providing safe drinking water for all.